Hi, can you hear me online?
Yes, sir.
Yes. Okay. Okay. So Aditya, which problem are you talking about? So a circle is given, point and line. And so you want to construct a circle which is orthogonal to given circle, passing to the point and center lies on the line. So I think we discussed this problem last time. Yes. Okay. So
Sir, you
where
cannot share your screen.
I am sharing actually, you are not able to see.
No, sir.
Sir, we can see the screen but not the board.
Oh, okay. So you are able to see the desktop. You want to
Yes,
say?
sir.
I see. I'll just stop sharing. I don't know what's the issue. Mhm. Still, I think you might be seeing the desktop only, right? On the.
Yes, sir.
Let me just reopen sensor board. So what are you able to see on the desktop?
There's just 3 files on the desk.
Okay, okay. So I think I shared the wrong screen. I think you can see the board now.
Yes, sir.
Okay. So so we're talking about this problem which we already discussed last time. Circle orthogonal to these three objects. Not orthogonal, but point lying on this line, center lying on the line, orthogonal to the given circle, and passing through the point P. So as we discussed last time, we can treat this P as a point circle, right? Circle with zero radius. And so what we know is that if there is a circle which is orthogonal to two circles, its center has to lie on the radical axis of those two objects. So the radical axis of this circle and this point circle. And if we construct that, then wherever it meets the line L, that is the center of our desired circle, right? If I join this point with this line, and if I draw the common tangents, and I take the midpoint of those tangents, then wherever that, so this is the radical axis of this circle and the point, and so this will be the center of our circle, right? Okay, so I sent a few problems for you to consider. Were you able to solve them? 5 problems. No. Which ones were you able to solve? Which we were not able to solve? So we can start with question 1. So question 1 was about. Actually, this is a standard formula, OI square. Maybe some of you. It is Euler's theorem, correct? So I don't know. Have you already done this in your regular lectures? No. Okay. But we can do.
Sir, we did this in our MPI online workshop.
Online also. Some people are saying they don't know it. So anyway, you can revise it once if you have already done it. So we are interested in finding OI square, right? So for those who have already done this problem, can you tell me what is the approach that can be used?
Power of I in two different ways.
Yes, power of point I in 2 different ways, because we are interested in the power with respect to which circle? The circumcircle, right? Yeah. So we consider the power of I with respect to the circumcircle, and we know that because we already know the formula for the power. Not a very good sign. It's very hard to get an intuition of how good is the circle if you are standing this close. So if we denote the power of I with respect to the circumcircle, as usual, we denote it by I subscript gamma. So if I call this circumcircle as gamma, then we know that this is going to be equal to r square minus d square. Actually, it is d square minus r square, but because the point is inside, we know that the sign is going to be negative. So we can compensate for that. And so it is going to be r square. So the radius of a circumcircle minus OI. And so in this, if I know this quantity, if I know what is I gamma, then we can find OI square. So we just need to compute the power of I with respect to the circumcircle. And so obviously, this AI, if I join, do you know anything about this point? Okay, this is a standard point, which is also the center of that midpoint of that arc, right? Minor arc BC. And so there are a lot of properties related to this point L, which you may already be aware of. So therefore, if I compute AI into IL, I will be done. So each of those lengths, AI and IL, do we know anything about those lengths which can be used? So for example, IL, does anybody know any property about IL? Yes, correct. So L is equidistant from BIC, all three. Okay. If any of you doesn't know this property, or you have done this but you have forgotten, then you have to go back and revise. Okay. But if you use this property that all these 3 lengths are equal. Okay. So BL. So therefore IL can be equated to BL. But what about AI?
We can show that triangles AFI and L in that area.
Okay. It's all the whole diagram. Okay.
We can show that triangle AFI and L here are
So F is the point
F is bit of the perpendicular from I on A.
A. So I think this is standard notation that everybody uses, that we use the letters DEF to denote the fit of the perpendiculars. So your claim is that triangle AIF, and which triangle?
AFI and L
L dash CL or L dash BL, doesn't matter. They are in the same, right? Okay. So does everybody see why these 2 triangles are going to be similar? Because they are 90-degree triangles, at one angle is going to be equal, right? Because if you look at this angle, this angle, which is going to be equal to the same angle inscribed in this arc. So therefore, these two triangles will be similar. And so if you equate the ratios, see, important thing is, why did you think of using this triangle and not any other triangle?
But I heard that we will get both R as well as smaller.
Right. Yes, because here IF is smaller and this big triangle has capital R. Okay, correct. Or maybe one more way to put it is that I'm interested in the length AI, right? So I need to relate AI with something else, and in particular AI and IL. So or rather now BL actually. So AI and BL, how can I relate those two? So we have to look for some triangles which have both those segments, and this is any property which connects those two. Okay. So if you write the ratios, we'll get what you want. AF upon L dash B is equal to AI upon. Okay. And so now here, if you see, we are going to get AI into BL. And that is IF into LL dash. And so here, if you see, IF is just the in radius, and this is the diameter of the circumcircle. And so what I'm getting is that this quantity, and by the way, this was equal to this, right? Because BL and IL are equal. So therefore, this is equal to 2RR. So therefore, OI square is and very similarly, you can do the X circle I1 also, right? Almost the same kind of approach can be followed for I1. So what is the formula that we get for OI1 square? Yes. So, I mean, actually, if you look at the power expression, right? I don't know why this happens. So if I write the power expression of all the important points, so the power of I with respect to gamma is 2 times R into R. The power of I1 with respect to gamma. No, it is still 2R R1, right? This should be minus. Okay. And this 2R R1. So you see how the sign changes because the in center is going to be inside the circumcircle and the X centers are outside. By the way, have you tried to prove this ever? That why the in center has to be inside? Maybe it's obvious, but why does the X center have to be outside the circumcircle? So what if the external angular bisectors are intersecting within the circumcircle? Why can't that happen? Because otherwise, see, you will get this value, but after that, the next step, OI1 square, there should you consider the positive version or the negative version? So should you take plus 2RR or minus 2RR? Because if you think about it, that's the only difference between the formula for I and I1, right? Just the sign is different. So just think about it. Can you prove that the X center is always outside the triangle or the circumcircle? I mean, who knows? If you draw a really obtuse triangle, maybe that, because if you draw an obtuse triangle, you know the circumcircle keeps on increasing in radius, and your intuition is that the X center will also keep going far away, so that the X center is always outside that circumcircle. But can you be sure about that? So just think about that. Okay. So any other proof for this? Yes, Kana?
The X center is the reflection of I and L.
Yes, correct. That is one way which we can justify, right? Because we know that this L is the midpoint of I1. And so if you take a point inside the circle and take its reflection through L, you'll get a point outside the circle. It cannot be the case that there are 2 points who are both inside the circle, but their midpoint is on the circle. I mean, that will be look something very funny. Like if you have a point here and a point here, then its midpoint cannot be on the circle. That cannot happen, right? So that is one way to look at it. You can also think of it through angles, by the way. If you look at I mean, we all know what is the condition for 4 points to be cyclic, right? The opposite angles have to be 180. But you can extend that and think of what is the condition under which one point is inside the triangle formed by the other 3 points. So if you know, just imagine that 180-degree angle, if the sum of the two opposite angles is more than 180, then you can imagine that that 4 point is coming inside the circumcircle. And if that angle is more than 180, then that point is going outside the circumcircle. Okay, do you see this picture? So if I have any 4 points like this, okay, and if the opposite angles, I'm only looking at this angle x and y. So if x plus y is 180, then they are cyclic, obviously. But what if, let's say, x plus y is greater than 180? Then intuitively, you can see that what it means is that this point C is going to be inside this circumcircle, right? So if I draw this circle here, it doesn't look like that. I think here I've drawn the reverse case. Okay, so here, let's say x plus y is less than 180. Then this point C has to go outside that circle and vice versa. So it is not just, that is a special case that when the equality happens, the point is on the circumcircle, but this is the more general situation, right? So we can use that. Okay, any other proof of this OI square property? This is the only way to do it. If you learn some trigonometry, you can also apply what is called cosine rule. Okay, so we won't do it today, but just keep in mind that that is also one more approach we can apply later on. So what is the cosine rule and how do we apply it here? So basically we require in this triangle, right? Consider this triangle. Let me just draw the triangle separately. Okay, AIO. Okay. So I am interested in finding OI square. So if I know this angle, okay, and these two line segments, then I can apply cosine rule to find the answer. Okay. So again, if you are interested to study this on your own, you can do that. But with that also, we should get an answer, and that should tally with this. Okay. There is one more solution which is there, but I'm not going to. I'm going to wait. I'm not going to tell that solution immediately. Okay. Anything else to say about this question? Otherwise, we'll move on to the second question. So the second question was, how many were able to solve that one? That I1 connected to O and extended. Did you see that question? No. So did you try the question and you didn't get it, or haven't got a chance to try it? Okay. If you have not tried it, I'll give you some time to think. Okay. Because otherwise, I don't want to reveal the answer. So the question was like this: ABC, the angle bisector. We take the X center. I1. So the question says we join I1 to O and we extend it in such a way that you'll get some point here. Okay. So I1O is equal to OX. That is how this point X is constructed. And the question asks you to prove that, I think that IX, right? To prove that IX is 2R. Okay. So again, can you tell me who all have solved this question? Only you, nobody else? Anybody online? Om, you have solved it?
Yes, sir.
Okay. Okay. So this is actually a very simple question. So I'll just give you 5 minutes. You can solve it here. Not that difficult. The question is clear, right? It's just I'm taking the point X such that O is the midpoint of I1X. We'll just give some time for everybody to try this.
L is the midpoint of I1.
Mhm.
O is the midpoint of I1. So the midpoint.
Anyway, by the way, can you tell me your name again, everybody? I forgot. Mallar, Tommy, Shyam, Sarva. Okay, so do you see this is a fairly straightforward problem because we know that I1 midpoint is L, right? So this is just midpoint theorem basically because L is the midpoint of I1I and O is the midpoint of I1X. So therefore, in fact, IX is going to be parallel to OL and IX is also twice of OL. But as usual, the question wasn't difficult, but there is a reason why I put this question, right? What ideas come to your mind because the fact that Ix is 2 times R, does that lead you to any? See, that this is why I want you to solve the problems beforehand. I mean, we can do the problems in class, but then I can't give you too much time to think after that. That Ix is equal to 2R. So what? I mean, do you think it is? Mm-hmm. Hmm.
Sin to ID will be 2R.
Yes. So what Mallar is saying, let us extend this line xi, which you already know. Very difficult to know. I mean, no, when there is a lecture, there is no lecture, I need to specially take some time to practice on this board. What now? Let us. Okay. So on this orange line segment, do you see that I know Ix is 2R, Xi is 2R, and let Ix be. And ID is R. So therefore, Ix into ID is 2R. Okay, so what? Have you seen this quantity 2R anywhere else? What is that? Yes. It is the power of I with respect to the circumcircle, right? So what does this say?
Then X2D are consecutive.
Yes, which points are consecutively?
O, X, and D.
OXD.
No,
Oh.
no, one second.
Which points? Yes, Sam.
X, A, and D.
X, A, and DL are cyclic, correct? So because basically this IX into ID is also equal to IA into I. And so in fact, we are making use of the converse of the power theorem, right? The power theorem says if 4 points are concyclic, then that product is equal. But here, given that these two are equal, we are able to deduce that these points X, A, DL are cyclic. And so this should give you some ideas. There be one more proof of that power theorem for the power of I, OI square can be obtained in one more way. See, here we used this property that we knew that this is the power of that point I to deduce that the 4 points are cyclic. What if you can prove that cyclic fact independently? Then do you see you can take the reverse way? So we'll first prove that these points are cyclic, XADL are cyclic. Therefore, the power of IA into IL is equal to IX into ID. And therefore, IA into IL is 2RR. So that will give you one more way to approach OI square. But for that, you need to prove this cyclic fact independently without using this approach. And you know, maybe many ways to look at cyclic quadrilaterals, like you can chase angles. There are many other things available. So I'll leave this as homework for you, but that will lead you to very interesting different proof. Okay. So prove that XADL are cyclic without referring to the power of I. It can be done. Point is just the foot of the point where the incircle touches. So this IX, because of this fact, right? IX is parallel to OL. So this is going to be perpendicular, right? So if I extend XI wherever it meets the base BC, that will be the point where the incircle touches that side. So do you see there was a connection between question 1 and question 2? They look like independent question, but question 2 will allow you to find one more proof of question 1. So think about this when you go back home. Okay, this was question 2. Question 3. Yes, Om, you have solved it?
Yes, sir.
Okay, just 1 minute. Who all have solved it? Om has solved it. Ruhan, Pranav, Mallar. Okay. Others not tried it. I mean, it's a simple question that if you try it, you will get it. This is a problem. You cannot using the board. In the normal board, you are accustomed to placing your hand as a pivot to stabilize your hand. You cannot do that here. Okay, so this is the setup. We have considered a circle with diameter AB, and to prove that circle PCD, and you'll often see this sort notation, right? Like circle with a dot to show the circumcircle of PCD is orthogonal to the given circle gamma. So I'll just give you another 5 minutes for you to think for those who have not solved this question. But for those who have solved this question, just think of the implications again, that because of this property, what else can you say? Many of these questions are just a starting point for some other train of thought.
In triangle ABC,
Mhm.
this is these two circles will be orthogonal.
Yes, correct. Yeah, correct. And not only these two circles, any other circles. So basically, any. Okay, not orthogonal. Yes, you are correct. Okay, so how do we do this? Yes, Om.
Yes, sir. First we join CD
Okay.
and center of circle means AB is midpoint O1 and the center of PCD is O2.
Okay.
Then sir we join O2D and extend some.
O2D. Okay.
That's it. Okay. Yes, sir. So let means angle ABD is equal to DCP because cyclic points.
Correct. ABD is equal to angle DCP. Correct. Okay.
Then sir angle DO2P is equal to 2 times that angle because it center.
Correct. Correct. So DCP will be, or we can say this will be half of angle DO2P. Correct.
Yes, sir.
Okay.
And so therefore by angle sum property as a O2D is equal to O2P. So
Yes.
angle O2DP is equal to 90 minus angle ABD.
No,
Means
sir.
original.
No, I didn't follow that.
Means if we calculate O2DP,
Okay.
it comes 90 minus angle DCP.
Yes, correct. So angle O2DP will be 90 minus angle DCP. Correct.
Yes, sir. And that's DCP is equal to angle ABD.
Yes, correct.
And as we means O2D and PD is straight lines, so angle BD or means that side. I mean, if
You want
we extend O to D to a E point, the intersect. Yes, yes.
okay.
Then angle EDB also be 90 minus angle ABD.
Will EDB will be equal to this angle O2DP, this one which you computed, which is equal to 90 minus ABD.
Yes. And sir, if we joined AD,
Okay.
so as the AB is diameter, so angle BAD 90 is equal to 90 minus angle ABD.
Yes, correct.
And so by alternate tangent theorem, it will be tangent.
Wait, no. So again, angle DAB is equal to how much?
90 minus angle ABD.
Angle ABD. Yes, correct.
So therefore, angle DAB is equal to EDB.
Equals EDB, correct.
And so therefore, D is a tangent to circle. By alternate tangent theorem.
Okay. So you are saying,
Yes.
okay. So I think my diagram is, I mean, this, if it's a tangent, my diagram should not look like this, right? This DE should, there should not be another point of intersection.
No,
Like
no, sir. It's any point of that line. Any point on that line.
any point on that. Okay. So maybe just need to redraw the diagram slightly to show that properly. Yeah, actually, knowing that the two circles are going to be orthogonal, the choice of point O2 was not that good. So point O2 may be somewhere over here. So that, this line, this looks like a tangent.
Yes, sir. So D is a tangent, and then we can prove that it's orthogonal. Two circles are orthogonal.
Because the line passing through the one center of one circle is tangent to the other circle. Well, interesting. So yeah, I've never seen this proof before. Let me just summarize it a little bit so that we can understand what is the strategy to be followed. What do we need to show and how do we need to backtrack from that? That is very important. The details are not that important, which angle we choose to show equal to which angle. We want to show that these two circles are orthogonal. So as we discussed last time, orthogonality can be characterized in so many different ways. For example, you have the formula where the distance of the centers, right? That is equal to R1 square plus R2 square. Or the most straightforward definition of orthogonality, that where the two circles intersect, there the tangent should be 90 degrees to each other. Or one more characterization is that the tangent at that point should pass to the center of the other circle. So all those interpretations are there. So in this proof, we are going to use that interpretation, that that tangent passes through the center of the other circle. And so what Ohm constructed is this line O2D. And if we show that this O2D is a tangent to this original circle gamma, then we are done. Okay. So that was the objective, that we want to show that O2D is the tangent that way. So revisiting the problem in that context, in fact, let me draw the diagram again. And let me take this point slightly off center. Okay, so the point D is over here. And so if this is the position of O2, okay, then this line O2D, I would like to show that this O2D is a tangent to the circle. Okay? And so therefore that is equivalent to showing that, suppose I take point E over here. So to prove that line O2D is tangent to gamma. So first, does everybody agree that this is an equivalent statement? If we prove this statement, it will also imply the orthogonality. And so now that this is what you have to prove, so continue to simplify this into something equivalent statement. So here, can we think of tangent secant theorem, that if I prove that this angle EDB, so this is equivalent to prove that angle EDB equals any angle inscribed in this RDB. So for example, DAB. Okay. So if we prove this, it will imply the original result. Okay. And then after that, there could be so many ways to proceed, that how you compute the left hand side, how you compute the right hand side. So in his approach, for example, what he has taken is he considered angle O2DP, this angle, which is equal to half of this angle. So if I call this angle X, then we know that this angle, so the central angle is 180 minus 2x. And so this angle is 90 minus x. And so this angle is also 90 minus x. And so in this triangle, this angle is also equal to this. Okay. So the details of angle chasing are not that important, but the strategy was the most important part of this proof. Okay, does everybody follow that? How you formulate the strategy, what you want to show. And as you can imagine, we use one interpretation of orthogonality. If you choose a different interpretation, that will give you a different proof. So does anybody have a different proof than this one? Rohan or Kano? Anybody has a different proof?
Yes, I assumed angle O1, O2, C, and the center of gamma to be X and no, sorry, I assumed angle D. I assumed angle O1CB to be X and showed that BCO2 is 90 minus X.
Okay. Yeah. So again, very straightforward approach, that if you just join the, so we know that this O2, O1 are the centers of the circles. And so, and we know that C is the point of intersection of those two circles. So if I just join O2C and O1C, then I'm interested in showing that this angle is 90 degrees, right? If I show that, then also we are done. And so then again, the details are not important, but the strategy is important, that this is how you can proceed. So if you show that, so to prove that angle O2CD and angle O1CD, they add up to 90 degrees. That will also give you the same result. Okay. Any other approach that you can think of? So believe it or not, you have visited this configuration many times when you did your previous lectures at MPI, or wherever you have studied basic geometry. Orthic configuration. Do you see that orthic configuration is there in this diagram? If I just relabel the points in some way, that orthic configuration will start to become visible. Because the same information can be disguised in so many ways, that this, talking about a circle with diameter AB on which the points C and D lie. Equivalently, I can also say that I'm just taking the fit of the altitudes from B to the opposite side. So if I just show this, look at this line. So this is already shown to be 90 degrees. In the same way, this angle is also 90 degrees. So let me redraw the whole diagram once more, but now starting with the orthic configuration. Okay. So we will relabel the points along the way. So the point P which was given there, let us call that point A. Okay, so this base diameter AB, which in the original diagram was there below, which is replaced by this line BC, right? And now we consider the fit of the altitudes. What do we typically call the fit of the altitudes? Is there any standard notation? Oh, we call them also dA. Generally, we use DF for the encircled points, right? It's okay. So, but do you see that this diagram on the right and the diagram on the left are really the same diagram with just relabeling the points. So the points C and D in the original diagram, they have been replaced by these points D, E, and F. And so what we want to show here was really that the circumcircle of AEF. So this is the orthocenter H. So can you tell me what is the circumcircle of AEF? Is there another way of describing that circle?
Center of triangle DF.
X center of triangle DFE, correct? Any other way? No, wait. What is X center of? A is the X center, but what about this circle? AFH, and or in other words, it's the circle with diameter AH, correct? So this is also the circle with diameter. So in other words, what is its center going to be? AH. And do we know anything about the midpoint of AH? That's the name, but do you know anything about it? X, yes, correct. But more important, lies on the 9-point circle, right? This is one of the points on the 9-point circle. And so it's interesting that the center of one circle we are considering lies on the 9-point circle. Okay. What about the other circle we are interested in talking about? Right. So in the original question, we were considering two circles, circle PCD and then this circle with diameter AB. So that circle is now the circle with diameter BC, right? So if I draw that circle, or I don't need to draw, but what is the center of that circle going to be?
Midpoint of BC.
Right. Let me. So circle 1 had center X and the circle 2. So circle BFEC, right? So its center is going to be M. And now coming to what we want to show, orthogonality, right? So what is the equivalent statement of orthogonality now? Suppose I say that give some names to the radii. Okay. Generally reserve the variables R1, R2 for the in circle and X circle, but for now let us just use those terms. So if this radius is R1 and this radius is R2, then to prove the orthogonality, what do we need to prove? That the centers of the two circles, xm square is equal to R1 square plus R2 square. If I prove this, then we are done. And is that obvious? Why?
Because X, E and or few of them that and XM is the diameter.
Correct. xm is the diameter of the 9-point circle. Therefore, this is fairly straightforward. Okay, because xm is the diameter, so obviously, so in fact, that also implies that this is a 90-degree angle. So either way, it's the same thing, right? Because of the diameter property, this is a 90-degree angle. And so therefore, these two circles are orthogonal. So you see, every interpretation of the orthogonality can give a different proof. If you use the tangent property, you get a different proof. If you use the fact that the angle is 90 degrees, you get a different proof. If you use the fact that R1 square plus R2 square is equal to xm square, that gives a different proof. And again, as before, don't just stop at this property. When you go back and think about what are the other implications of this orthogonality, because this is very interesting that the circle AEF is orthogonal to this circle with diameter BC. And similarly, you will get orthogonality on the other two sides also. So in the same diagram, the circle with diameter BH and AC are orthogonal, correct? So if I just write all those properties together, and so circle, I don't know if there is any special symbol. Let us just invent this symbol, okay? So this is the notation I'm going to use to denote a circle with diameter AH. Okay? This is just a circle with diameter AH. It's not standard notation by any means, but just to make our calculation easier. So my claim is that the circle with diameter AH is orthogonal to the circle with diameter BC. And same with BH and CH. So we have 6 such circles we are considering, and pairwise they are orthogonal: AH, BH, CH. And so when you go home, you can start to ask questions like, what are the radical axes of, if you take any 2 circles, what is the radical axis going to be? And then we know some properties, right? If there is a circle which is orthogonal to 2 circles, then its center has to lie on that radical axis. So that will also lead to some interesting properties. So what I'm really showing is that you already studied orthogonal orthic configuration very well, but what you have discovered are only half of the properties. The remaining half properties, because of the power of a point, you are going to discover. Okay. Okay, that's all on this question. Then the question 4. Anybody who has solved question 4? Anybody online? No. Okay. But again, it is related to orthic configuration only, because what we have is so X is the midpoint of AH as usual. Then we are considering a line passing through A and perpendicular to OH. So this is what we call line L. And let it intersect the base at some point. Okay, so we are calling this point R. And our claim is that if I take the feet of the altitudes, right? So here I only drawn one altitude, but suppose I draw the other 2 as well. Then my claim is that PF are a collinear. Okay, so again, I'll give you some time to think, at least 10 minutes actually. पंखा हवा कोणाला 2 वर्ष So this is where what starts to matter is, do you have a good working toolkit to prove collinearity? When you want to prove 3 points are collinear, what are the various approaches you know? Menelau's theorem is one approach, certainly. Any other approach? Linear pair. If you show that there's some supplementary angles are there, that will also imply collinearity. Any other approach that can?
Points,
Sorry?
phantom points.
Phantom points. What does that mean?
So to prove that RF and E are collinear, we extend RF to meet AC at some other point, and then we prove that that point is the same as E.
Yes, correct. Okay. So you can reverse the problem. And just for symmetry, let's do it the other way. Instead of extending RF to meet at E, let us extend EF and let it meet the base at some point. Right? So we can say let EF meet. So let EF meet BC at some point R dash. So let me erase this blue line temporarily. And let me draw this line instead. And we are interested in showing that this R dash and that R are the same point, right? And so that to achieve that, what do we need to show? What property should this R dash satisfy? Yeah, no, that is a much more complicated step. As a first step, what was given about that point R was that it is on this line, right? So what do we need to, if we reverse that, what do we need to show? Correct. So if we prove that AR dash is perpendicular to OA, right? If AR dash is perpendicular to OX, it means that this line, like AR dash is the same as this blue line, right? Which I've drawn. Correct? So Mallar, I already finished the question? No, but you basically gave the answer. So as a first thing, this is one way to rewrite the problem, right? Instead of the original question, we have a different question now that let EF extended meet the base at some point R dash. Now prove that R dash A is that perpendicular line to OX. But just because you can rewrite the question like this doesn't automatically mean that is going to be helpful. Sometimes you rewrite the question and make it actually harder than the original problem. So how do we know that we are on the right track? Right now, we don't know. We have to experiment and find out. So through this diagram. So Kanav, are you able to take this forward and finish the question or not yet?
Not yet.
Okay. But at least the one proof which I know, it is on the right track with this one. And remember, the topic is power of a point. So again, this is a luxury that you have, that you know the topic is power of a point. So you have to use power. If this was an exam question, nobody is going to come and tell you that try to use power. So maybe start by thinking of all the properties you know about orthic configuration. Like the particular point X, we also saw that point X in the previous problem, right? So what property about that point X you think can be?
We can use the fact that FHEA is a like a cyclic quadrilateral, and we have to find the power of point O with respect to this circle, the circumcircle of it.
Yes, which circle are you referring to, Anushka? Again,
Of the quadrilateral FHEA.
FHEA, correct. So we know what we saw last time, right? X is the center of that circle. So X is the center of X is the center.
EF and AH.
And O is the center of the circumcircle, obviously. And so you see how all the parts are relating to each other, that we have line OX. So you see OX is the line joining the centers of two circles. Correct? So if I just draw two circles here, these are not those circles, but in general, suppose there are some two circles, centers are given as X and O, and you are talking about the line joining them. And no, in fact, these are intersecting circles, right? They are not like that. Let me draw them as intersecting circles. Still not happy. Something like this. Let us say this point is A. So this is the setup. See, this diagram was hidden inside that big diagram, but because of so many other things, it is hard to spot the important part. But now, having isolated just the part which is important to us, do you start to see that the what we are asked to prove, this line OX, which is the line joining the centers, okay, and then to that we are constructing this perpendicular line. So this line which was perpendicular. So see what kind of line it is. That blue line. Can you describe that blue line in some different way now? In this diagram. From A, we are drawing a perpendicular to this. You see, it is a common chord of these two circles actually. When you take the point of intersection of two circles and you draw a perpendicular to the line joining the centers, you're actually talking about this common chord, right? So it's actually going to pass through the second point of intersection also. So you do see this is how examiners disguise the question. I could have told you that consider the common chord of these two circles, but I didn't say that. I said consider the point A and draw the perpendicular and let that meet the base at some point. But actually what I'm talking about is the common chord. And so what I have to prove here that AR dash is perpendicular to OX. So what I want to show is that R dash also lies on that same common chord. And what is the common chord when two circles are involved? It is the radical axis. So I want to show that R dash lies on the radical axis of these two circles. Is this clear or any doubts what we are doing here? So you see we are combining 2-3 small properties that we studied before. The fact that the common chord of two circles is the radical axis. Then that radical axis is perpendicular to the line joining the centers. And then this is a basic property in intersecting circles, that the perpendicular bisector of that common chord is the line joining the centers. Okay, so therefore, it's enough to prove that R dash lies on the common chord of these two circles, right? Or in other words, so it is enough to prove that R dash has equal power with respect to these two circles. Actually, this is a problem. Can we split the screen into two parts so that the diagram remains constant and I can just scroll the text? Because now the diagram is not visible. We have to solve this somehow. Yes, but I have to keep moving it every time, right?
So, sir, I think you can copy that diagram and paste it down again.
Yes, that is there. But I would like to split screen view where half the screen is always visible, and the right half I can keep writing. That would be ideal. But anyway, for now we have to live with it. Okay, so let me just for me the reverse is easier. Let me copy that sentence here. Okay, that is easier for me. So now does everybody understand the new objective? That we have equivalent, we have shown that it is equivalent to prove that R dash has equal power with respect to the two circles AF, HE and the circumcircle. And is that true? Sorry.
For R dash B into RC will be R dash F into.
Correct. So the circles we are talking about, first circle is this one, right? It's center X. And the other circle is the circumcircle, of course. So this orange and green circles, I would like R dash to have equal power with respect to both of these circles. So what is the power of R dash with respect to circle ABC? The power of R dash with respect to circle ABC.
RF into RE.
No, ABC.
I'm sorry.
RB into RC, right?
RB into RC. Yes.
R dash B into R dash. And what is the power of the circle with respect to other circle?
RF into RE.
Correct.
So now we can use similarity, right? Or
Similarity or even more directly, you see these two quantities have to be equal because we have one more cyclic quadrilateral in the diagram. BFEC. Do you see that same BFEC was there in the previous question also? So because of that BFEC circle, so these two quantities are equal. And so therefore, this is equal to this. So just revise the whole proof in your mind once more. From the starting question, how did we keep on modifying the question one step at a time to get this final question, or the final solution? So if I just summarize those important steps in one place, we'll just give 1 minute for you to copy if you want. So, kind of a summary of what we wanted to prove. So the question had asked to prove that. So original question, there we did not take the phantom point, right? There we took that line perpendicular to, so there it was given that AR perpendicular to OX, and to prove that RF ER collinear. So first step we did was consider that phantom point. we constructed R dash such that EF R dash are collinear. And so we reverse the question. So given that R dash FE are collinear, prove that R dash O, AR dash perpendicular to OX. This was the first step. Then the next important observation was the fact that this the line perpendicular to OX, right? So line perpendicular to OX and passing through A is the common chord and not only a common chord, hence it's also the radical axis of those two circles, right? This was the next important conclusion. And therefore, what the conclusion of these two was that therefore it's enough to prove that the power of R dash with respect to these two circles is equal. And finally, the last step was just observing that we have one more circle in our diagram. We use the circle BFEC to show that these are equal. So these were the 4 important steps involved in this question. So understand that Olympiad problems are always like this. It looks like one complicated question, but it has 3-4 simple parts to it. You know, if I ask you to prove one step at a time, everybody will get it. If I ask you to prove that this line perpendicular to OX is the radical axis, that part is easy because that is just one step. But combining these 3-4 steps together gives you the full question. So this is what you need to practice, that how do you break a bigger problem into smaller problems. And this is the most important idea. Keep rewriting the problem into equivalent, simpler version. You know, keep rewriting the problem. Keep throwing away information which is not important at the given moment. You know, there may be many extra points in the diagram which are just there to confuse or disguise the problem. But you should know which part you want to focus. Okay. Okay, anything else about this question? Actually, this is a very rich configuration. This has so many properties. If you see, this is just one part. That question has another part also, right? Did you see that? So here, all we have showed is that these 3 points are collinear, R dash FE. But you can do the same construction on the other 2 sides also. Like, for example, if I extend DF, let it meet the base at another point S. And finally, this ED will meet this at some point T. So there are 3 points, R, S, and T, that we are considering. And so the claim is that all these 3 points are going to be collinear. Why? Because actually, if you look at this diagram, so this R was on the radical axis of this green and orange circle. But do you see it is also on the radical axis of many other circles? For example, consider this one more circle. Our BFEC, obviously. Yes. So if you look at this, anytime 2 circles intersect, their common chord is the radical axis. So the circle with diameter BC, which is BFEC, and the circumcircle. So their common chord is this one, right? Side BC. So R lies on that line also. R also lies on EF. And can you think of any other circle which passes through EF? DF, the 9-point circle. So in fact, what we are saying is that R is just write it. So the claim we are making is in fact that R lies on the radical axis of the circumcircle and the 9-point circle. And if you think about it, this statement is perfectly symmetric in terms of ABC. Here we are just talking about the radical axis of the main circle and 9-point circle. The diagram was constructed with taking the base BC, but if you take the same diagram with base CA or AB, whatever points you obtain, they will also have the same property. So just as R was constructed as the point where EF meet the base BC, right? So in a very similar way, so R was intersection of EF with the base BC. But similarly, you can consider points S and T. Then all RST, all of them will satisfy the same property. So in fact, line RST is the radical axis of the circle and the 9 points. Okay, and there is a special name here to this line. It is called the orthic axis. Any other interesting observation about this line that you can make? So radical axis is perpendicular to the line joining the centers of your circles, right? So what are the centers of these two circles? Huh. So what is that line joining them? Do you know any name for that line?
So Euler line.
Euler is a more correct one. Euler line.
Euler line is perpendicular to orthic axis.
Yes, correct. So that Euler line has all the 4 points: orthocenter, circumcenter, 9-point center, and centroid. So that line will be perpendicular to the orthic axis. Why? Because that line is the line of centers of these two circles. Okay, so the orthic axis is actually perpendicular to the Euler line. And in our diagram, it roughly looks like that also, right? I mean, here we are not constructed the full line, but essentially, roughly speaking, if you look at this OH, so OH is my Euler line, and this RST are going to be perpendicular to that. So wherever T is there, we cannot draw T in the diagram. And there are many more properties. So keep exploring, try to find as many properties as you can on your own. Okay, so then question 5. You have solved this question?
Yes, sir. Sir, I solved using cosine rule.
We solved it using cosine rule. Okay. I don't remember the solution, so I will also have to prove it again. So here we are considering the power of, so let the 9-point circle, let us use the letter gamma be the 9-point circle. Then by standard notation, we know we write A subscript gamma to denote the power of A with respect to that circle. So we are interested to compute this. And the claim is that this is equal to 1/4 of you are done this? Okay. You have to use trigonometry or you did it with pure geometry? Okay, okay. Yes. But then do you know the proof of that one? Without trigonometry, with trigonometry? With not. Okay. I will just have to think it. Orthic axis. So Om, when you say cosine rule, actually if you think about it, cosine rule can be replaced by the generalization of Pythagoras theorem, right?
Yes, sir.
So in that sense, maybe you don't require the cos A, cos B, cos C terms, right? If you think about it. Anybody else has solved? Rohan, Kanav, you also solved this problem?
Yes.
Okay. So does your approach use basic like geometry or trigonometry, anything like that?
I didn't use
Geometry.
trigonometry.
Okay. So we can start by finding one term, right? Let us just find the power of A with respect to the 9-point circle. Okay. So let us say you want to first step is to find this term, power of A with respect to 9-point circle. So there are multiple interpretations. One is that you can use the d square minus r square, but that is not necessarily the always what you have to use. You can use some other property also. Like basic definition of power is just product of that chord, right? So if you consider some suitable chord where you can compute that distance ax into ay, some points x and y. So which points can we take? If we are talking about the 9-point circle, which points can I take?
Sir, base of altitude and midpoint.
Yes. So we have multiple options here. So what Aditya is saying, you can consider the ax and ah, right? If I take this ax and ad, so ax into ad can be one option. But one more option can be much simply if I just take the midpoint of one side and the foot of the altitude, right? Let me take the other one. So if I consider the midpoint of side AC and this point, let me call it M, then you see the power can be very simply written as A into AM. So if I compute AE and AM, I'll get this power, right? And out of that, AM is obviously just B by 2. So only thing left to compute is AE. And how can you compute AE? So which theorem property do you know in which that length AE is involved? Anybody online? AE F, yes. Yeah, that is true. Something much more direct. Because finally look at the question. There we are finally want to find the answer in terms of small a, small b, small c. Pythagoras theorem. But not Pythagoras theorem, but what else? Do you know extension of Pythagoras theorem to acute and obtuse angle triangles? So assuming that it's an acute triangle, then
So AE will be cos AB, means AB cos A.
yes, correct.
Like
And that cos A has to be replaced by something else, right?
yes.
So instead of doing that, I'm saying we can do both of them in one step. Yes, Raghav.
Sir, actually, I don't think we need the Pythagoras theorem.
Okay, then suggest what any other way you have.
Yes, sir. So like if you do not say so M is the midpoint of AC, then you
Yes.
can say N is the midpoint of AB.
Okay.
So
Yes.
now if you so now we have AM times AC equals AN times AB.
Yes.
So the power of point would be half the sum of these two.
So can you repeat that?
So we have, you know, that AM times AC, sorry, I
Yes.
mean, sorry, AE times AC,
E times AC.
sorry, sir, 1 second, my bad. I named the figure a bit differently in my, the perpendicular, can you also draw the perpendicular from C to AB?
Let me call that point A.
Yes, sir. So now we have, because of power of a point,
Yes.
AE times AM
E times AM.
is equal to AF times AN.
Yes, correct.
So the power of point of A with respect to the 9-point circle
Yes.
would be half of the sum of these two.
Okay, yeah, interesting. Correct. So this will be sum of these two. Upon two. Okay. Then
Yes. So now this is basically AE would remain like that only. AM would be B by 2
yes.
and AN would be C by 2.
Yes, correct. So here we'll get B by 2 and C by 2 in two places.
Yes,
So
sir.
I'll get
So we
A
have B times AE
B times AE.
plus C times AF
A
upon 4. Now you can do the same for the other 2 points
Okay.
and then you'll get the result.
Yes, interesting, because actually AE on one side and other side will have C. So those half will add together. Interesting. So are you following the Raghav strategy? That what he observed is that we don't actually need to compute the distances, actual values of the distances. Does this happen with everybody, or I'm making some mistake? So we are interested in finding the sum of all three powers. So what he did, he took the power of A with respect to 9-point circle. First, do you agree that this statement that A into AM and AF into AN will be equal, because we are forming a actually, or you can say that they are both going to be equal to half of the whole product, AE into AC. So term by term, if you see AE into AM is going to be half of AE into AC, simply because M is the midpoint of AC. And similarly, the other product AF into AM will be half of AF into AB. And then do you see that these two will be equal because of BFEC? These two will be equal. Therefore, these two are equal. Okay. And so therefore, if you want to find the value of any one of them, you can take their average. So he wrote the power as the first term plus second term upon 2. Okay. This seems like a trivial manipulation, that this is obviously true, but what it does is it helps us later on, because now having done that, out of that, this AM and AN, they are just half of those respective sides. So we can replace them by B by 2 and C by 2. And therefore, A power of A with respect to gamma, we got this expression, correct? And now if you write the same expression with respect to B and C, do you see what will happen? That this term, which is B times AE, right? So B times AE, a very similar term will come, which will be B times CE. And when you add them, AE and EC will add and become B square. Okay. So that in hindsight, we didn't know that, but thankfully, luckily it turned out that way, that we can take things common and we get the answer. Okay. So continuing to write the next terms. So B of gamma will be very similarly, it will be C times BF plus A times BD upon. So here itself, when you see, if you add these two together, C, these two terms are going to combine, right? C times AF and C times BF together will give you C square. And like that, all the 6 terms will be combined pairwise and you will get the answer. Okay, do you see that? So this AE and this will group together, and finally this will also group together. This and this. So when you add all them together and regroup it, you are going to get adding all them, you will get the answer. Okay, does everybody follow this proof? But suppose you could not think of this, clever trick. We still want to do the question. So going back to the original approach, where we had reached this point. So we said that the power of here. So rewinding just for a moment and coming back to this. When we had reached this point, right, AE into AM, and here we could say that AM is B by 2, right? But we don't know what about AE. So there, I suggested, can you think of some property which involves the length AE? So for that, you can think of extension of Pythagoras theorem, and specifically which side will you try to write? For example, let us try to write the side BC. Okay. So what is the Pythagoras theorem for side BC? So BC square is equal to BA square plus AC square. So what is the extension of Pythagoras theorem? First you write Pythagoras theorem, and then you have some adjustment term. So what is that adjustment term going to be? I hope you have studied this, right? No, I mean, looking at your faces, I don't know whether you have studied or you have forgotten.
Sir, minus 2 times BD into BC.
BD into BC, but here we are interested in AE, right? So let us use it that other altitude.
Okay.
AE into this, right? So how to remember this easily. First write Pythagoras theorem, and then for acute angle triangle we subtract. How much do we subtract? We have to take the length of the side and the length of the projection of the other side. So because we are computing BC, so the other side is BA. So how much is the shadow of BA onto this? So that is AE. So that is how that term comes about. And if you know cosine rule, you say exactly, I mean, what Ohm you are saying, right? Cosine rule will give you the same thing, right? So now here you see everything is in terms of the sides of the triangle except AE. So can you rearrange this now and give AE in terms of the sides of the triangle? So how much is AE? It will be C square plus B square minus A square upon 2B. Correct? This is AE. And then finally combining this and this, you'll get the power of A with respect to gamma will be this into B by 2. And so do you see that B, the denominator B and B by 2 are going to cancel. And so what you're going to left with is C square plus B square minus A square by 2. Right? And now here you see similar by symmetry. Here you have 2 positive and 1 negative. So like cyclically one term will cancel. And so finally you get the sigma as okay. But the property which Raghav mentioned is interesting, that you can use a nice trick like that, that you don't need to calculate the value of AE. Luckily, that goes away by that adjustment trick. So actually, make note of that trick. That is a very useful idea. It seems so trivial that we forget to use it. But if I have X and Y, then that X and Y are also equal to X plus Y by 2. Very trivially. And in fact, you can extend this, right? It is also equal to root of XY. And it is also equal to not only that, I mean, there is nothing special about X plus Y by 2. You can take the what we call weighted combination of X and Y in any ratio you want, right? So if X is equal to Y, if X is equal to Y, then X is equal to Y is equal to also any constant you can take multiply X with any constant you want, multiply Y with any constant you want, and divide by the same. And can you think of a very similar multiplicative property which will be true? How do you multiply X and Y? So obviously root XY is there, but why should we have to multiply X and Y with the same degree? So what can be the multiplicative equivalent of this way? Can we write something like this, which is also going to be equal to X raised to some power, Y raised to another power, and then you take the root of that same power. Okay. So these are trivial things, but they can be very useful in some problems. Okay, so those were all the questions that were discussed. We're almost towards the end of the lecture, but so let me give you, let's start with coaxial circles by one property, or rather one that locus problem, which we already shared last time. Okay, we'll solve that problem, and I'll encourage you to see how that leads to coaxial circles theory. Okay, and then when you go home, you can, I forgot to upload the video of the coaxial circles, but I'll do it today or tomorrow. So watch that video, and we'll discuss the theory next time. So coaxial circles. So the question 5 of that locus data set, right? So suppose given circles gamma 1 and gamma 2, and some real number k, okay, find the locus of points P such that power of P with respect to gamma 1 upon power of with respect to gamma 2. Okay. So we have done the problem of when that locus is equal, or when the powers are equal, that is the radical axis. By the way, when the power is, the difference is constant but non-zero, have you thought about that problem also? So when we say let power of P with respect to gamma 1 and P with respect to gamma 2, this is some constant k, and which may not be 0. So then what is the locus of that? It's a straight line, and it's like a shifting of that line. Do you see? As k changes, that line keeps on shifting left and right. So in the diagram looks something like this. So this is the radical axis. Okay, so the radical axis is the line where k is 0, right? Where the difference is 0. But if the, let us say, the power with respect to one circle increases, which direction the line, if k is positive, will the line go towards the first circle or the second circle? Actually, it will go to the right, right? So here it will be negative, and for here it will be positive, correct? So as the value of k changes, that line keeps shifting. And so actually there's a one-to-one correspondence between every value of k you can choose and this whole set of parallel lines in the plane. You know, any line you choose in this family, that will correspond to one value of k. Okay, so understand that one-to-one correspondence, that there is a bijection. You know the word bijection? there's a bijection between the set of real numbers and this family of lines. Got it? So in a very similar way, what we are taking here is not the difference of the powers, but the ratio of the powers. Okay. So power of p with respect to first circle upon power of p with respect to second circle. And now we are asking what is that locus going to be like? So has anybody already solved this question? In fact, we had solved the most general question of this kind. If you remember, in that, if you have watched the lecture, we had done, power of p with respect to gamma 1 into some constant plus power with respect to gamma 2 into some constant, etc. We had taken n circles also. So this is just a special case of that n circle situation, as such, if you think about it. So you can just take that general formula and substitute the right values, and you'll get this answer. But independently, let us try to prove this. Okay? Let us try to find this locus. So suppose some point P is given such that O1P, so point P is given such that it has this property. Okay. P gamma 1 is equal to K times P gamma 2. So given so if we write the expression of the power, we are also saying that O1P square minus R1 square. If I call this radii R1 and R2, this is K times minus R2. Correct? And so as usual, what is the first thing you can try to do when you have expression like this? If you remember what we did for the power radical axis question, correct? Take constants on one side and take the variables on the other side. So then we can rewrite this as O1P square minus K times O2P square is equal to R1 square minus K times R2 square. So the value on the RHS doesn't matter, it is some constant. So we have an expression of the type O1P square minus some K times O2P square is a constant. So again, see, this pattern will keep on happening, that you look at some problem, does it remind you of some other problem or some property which you know, which you can apply in this problem. Like in the case of radical axis, we thought of Pythagoras theorem. So here also it looks like something like Pythagoras theorem, but not exactly Pythagoras theorem. Pythagoras theorem has many cousins. Do you know all the cousins of Pythagoras theorem? Like what we saw in the previous question, that for acute triangle, obtuse triangle, there is a slight variation of Pythagoras theorem. Like that, what are the other cousins of Pythagoras theorem? Do you know? To give you a hint of what cousin I'm talking about, let me just take a special value of K. What if K is equal to -1? So just temporarily consider the special value of K. Right. So temporary, side exercise. What if K is equal to -1? Then what will this expression become? O1P square plus O2P square, right? So if K is -1, then for the time being, we are solving the question O1P square plus O2P square is some constant. So looking at the diagram, do you know any property which looks like this? No, I didn't follow. Which radical axis? No, forget the circles. You have just 3 points, O1, O2, and P. And I'm saying O1 P square plus O2 P square is equal to O1 and O2 are fixed, correct? So what? O1, O2 distance is constant, yes. So
1 p square plus 2 p square is equal to
what? It's not a right angle triangle. P can be any point in the plane. So again, looking at your expression, I don't know if you don't know that property or you know the property, but it is not occurring to you that you can use it here. Do you, O1 PO2 is constant, why? What does that have to do with the angle? Okay, I don't know. Either you don't know this property. So by the way, in a triangle, suppose I give you all the sides of the triangle. Can you find the lengths of the medians? How? So what is Apollonius theorem? So everybody knows it. So my fear was that I'm assuming that you don't know these things. Everybody knows this. What is Apollonius theorem? I've not drawn the median in the diagram, but with this expression, does it remind you of Apollonius theorem? So how can you use Apollonius theorem in this question now? For that, you need to construct a median, right? So which median should we construct? From P, right? So let's take the midpoint of O1, O2. So let's say M is the midpoint of O1, O2. And so by Apollonius theorem, what can we write? O1 P square plus O2 P square is equal to O1 O2 square, right? And you see interesting thing about here, this is also constant. O1 O2 square by 2 is also constant. So what are you getting?
center M and radius.
Yes. So the locus is a circle where the distance PM is going to be constant, right? So this constant, I just written constant here. We know this is that R1 square minus 8 times R2 square, right? So if I combine both this one and this one, what I'm going to get PM square is equal to O1 P square plus O2 P square minus, we'll call this D, right? So distance between O1 and O2, we'll call it D as usual. So D square upon 2, and which is equal to R1 square minus 8 times R2 square minus D square upon. Oh, sorry, I should not add K now. K is minus 1, right? So it's simply. So PM square is constant. And so it's a circle with center M. But see, this is what you need to practice. You know Apollonius theorem, but I don't know. When was the last time you revised Apollonius theorem? Maybe 1 day ago, 1 week ago, 1 year ago. I don't know. What is the time scale at which? Yes. So that is your responsibility. That all these tools should be available at your disposal. That I can see the term O1P square plus O2P square. The labels will be different. See, if I give the label ABC, then maybe it will occur to you immediately that is AB square plus BC square. But see, the exam paper will not be friendly to you that way, right? They will not make things easy for you. But that Apollonius theorem is there. And we could use that to solve this problem. But by the way, all of this was for the special case of k is equal to -1. So what if I remove that special case k is equal to -1? Which cousin of Apollonius theorem do you know now? Stewart's theorem. So so there's a whole family. Pythagoras theorem has first siblings like the extension of Pythagoras theorem. Slightly far away cousins like Apollonius theorem, and Apollonius theorem's cousin is Stewart's theorem. So through that relation, actually Pythagoras theorem is only related to all these things, if you think about it. But now that you have that idea in your mind that Stewart's theorem can be used, this is your homework. That go back and solve this problem now. This original problem of the locus. Like how will you use Stewart's theorem cleverly? Because you know that weight is important, right? Here the weight is 1 and here that weight is minus k. So which point you have to choose on that line over no 2 to get that ratio. That is important. Okay, but give it some thought. And so in fact, I have already covered this in the video which I have recorded. So we'll get the answer of that. But after that, I'll continue to develop coaxial circles theory. No, 34. And we'll take it forward in next lecture. Okay, so we have 10 minutes left. As I didn't do this last time, but generally I try to finish the lecture with some question, some problem, which is like a puzzle of some kind. Okay, because many times the puzzles motivate some ideas which are useful in problem solving. You know, basic logical thinking. How do you deal with the problem logically? So maybe, and some of you may already be knowing these puzzles. In that case, don't reveal the answer. Let others think and try the problem first. So and then this is a practical problem, by the way. This is a problem which is requires to be solved every day by millions of systems, millions of computers around the world. And that problem is that you want to send information to another person. Okay. And the question is, how much data do you require to transmit that information? Okay. That is what this question is about. So do you know binary numbers? That you know the letter 0 and 1. Numbers 0 and 1 are used to write everything. So you may be familiar with this idea. And so what we can do is, suppose a very simple language has only 4 letters, A, B, C, D. Okay. So you want to send A, B, C, D and some message which uses these 4 letters, A, B, C, D. Okay. And so what typically computers do, or systems do, is they will encode each letter with the binary symbol or a sequence of binary numbers. So for example, one can say let A be written by 00, let B be written by 01, C be written by 11, and D be written by 10. Okay. Very simple pattern. Okay, so if I want to talk to you and I want to say the word DBA. So instead of saying DBA, I will say 100100. Okay. So if you receive this string, can you decode and understand my message? Because what will you do? You will split it at boundaries of 2 symbols and you decode it. So this 10 will become D, this 0 will become B, and 0 will become A. Okay. So these are called symbols. And this is called the code. So each symbol has a code. Okay. And each letter 0 or 1 is called a bit. Do you know this term bit? So 0 and 1 are called bits. And so here, if you see, the question is how many bits are required per symbol? What is the answer? Every symbol is requiring 2 bits, right? 0, 0, 1, 0. So the answer is 2. Okay. So every symbol requires 2 bits to transmit the information. But if you just do some simple calculation and you think how much data it will require to transmit this way, you will come with a very big number, like maybe 100 Gbps connection are required everywhere. Or if you save your Word file, let us do this thing, open a Word file and just type ABCD 1,000 times and save that file. And just imagine what will be the size of that file and what is the actual size. You'll see that actual size is much smaller somehow. So there is some clever trick which you can use to transmit the same information. Information should not be lost, but you can do that using less number of symbols. So for example, consider this option. I'll give you a different symbol pattern. I represent A by 0, B by 1, C by 10, and D by 11. I can do that. And now I'll transmit my message. So now you yes, Anushka, we can't do that, but let everybody figure out why we can't do that. Okay. So can we do this? If I want to say A, I'll just say 0. If I want to say B, I'll just say 1. So let us say I want to say the same message, DBA. So the receiver will receive 1, 1, 0, 1, and sorry, 1, 1, 1, and 0, right? So this is the D. So this is what the transmitter is sending. He sent D, B, and A. It is not unique. You see the problem? Looking at this symbol, you don't know where to put the partitioning. Here, all the symbols are of the same length. So it was clear that, boundaries of multiples of 2, you will do the splitting. But now some symbols are of smaller length and some are of larger length. So you don't know where to split it. So somebody may have a different way to split. If you're luckily the other person split it in the right place, you'll get the same answer. But what if somebody splits it like this, 1, 1, 1, and 0? So they'll interpret it as BDA. So, this trick was clever. It reduced the number of bits required, but it is introducing another problem that you cannot decode it uniquely. So you require some solution which achieves both things. We'll have to send less number of bits, but you can always decode it uniquely. Okay. And if you solve this problem, you are going to save the energy required to transmit your message, or save that file to your hard disk or anything like that. Okay. So let us say, in English language, all letters don't come in the equal frequency, right? A, B, C, D up to Z. The vowels are much more frequent. A, E, I, O, U will come many times, and letter like Q or X or Z will be very infrequent. So suppose, we have that information that letter A is very frequently used. Let's say 50% of the times letter A is used. Then after that, letter B is used only 25% of the times, and letter C and D are used 12.5%. Okay. Suppose this extra information is given to you that A is occurring very, very frequently, B is occurring less frequently, and C is very, very, rare. So can we use this information to improve our strategy in some way? So naturally, what do you think we should do? The letter which is occurring most frequently, should we use more bits for that or less bits for that? Less bits, right? Because then we have to use less bits to send that information. And the letter which is occurring less frequently, we can use longer string for that. Correct? So, for example, can we do something like this? This is just one example. Let us say I use 0 to transmit A, I use 1, 0 to transmit B, I use 1, 0, 0 to transmit C, and I use 1, 0, 0, 0 to transmit D. Now you say this will be uniquely decodable because of the position of the 1. Oh no, will this be unique? No, let me do it this way. This will be unique if you think about it, because that 0 is acting like the full stop. Whenever the 0 comes, you know that one symbol has finished. So now suppose the same symbol is transmitted B, D, A. What will that become? So B will be 1, 0, D will be 1, 1, 1, 0, and A will be 0. So do you see there will be no problem decoding this, because the receiver knows that the 0 is the end of some symbol. So he will correctly put the partitions over here, right? So he'll interpret this as the first symbol, this as the second symbol, this as the third symbol, and there will be no ambiguity. So you see, this code does not have any ambiguity. So you see, every code has some pros and cons. So this first code has the advantage that all the bits, all the symbols are of the same size. This code, now if you see, all symbols are not of the same size. And now if you try to compute that, how many bits are you going to require to send the information? So suppose you have a letter, okay? So suppose I have a letter which has, as you know, the distribution of the letters is ABCD like this. So no, letter means not letter, letter. Will write dear sir, so whatever. So in that, let us say we have 1000 characters in that letter, and they are split in this manner. So 500 times you are going to use the letter A, 250 times you are going to use the letter B, and 125 times you are going to use the letter C and D. And so compute that if you use this strategy, let us say we'll call this code 0. If I use code 0, how many bits will I require to send this letter?
200, 2000.
2000. Because it doesn't matter which letter you use how many times, total 1000 characters you're sending, and each character or each symbol requires two bits. So this code 0 will require 2000 bits. What about code 1? So code 1, you can make a table over here, right? So code 1, letter A, which is occurring 500 times, but each occurrence uses only 1 bit. So total number of bits required to send A is 500 into 1, 500. Then letter B, which occurs 250 times, also, 250 times. But every time the letter B occurs, you have to use 2 bits, right? So, also fine. And what about C and D? So how much is that turning out to be?
375.
So the total is 1875.
Yes, 187.
Fine. So the total is 1875. So you see, you have saved information. Code 0 required 2000 bits to transmit, but code 1 can do the same job in 1875 bits. And it is still decodable uniquely. That is the important property. If somebody receives this string, there will be no confusion what the sender wanted to send. So you saved the energy required to transmit that message. Okay. So now your homework is, can you come with an even better code? Maybe you can save even more energy. Instead of 1875, maybe you can do it in 1500 bits. So the more efficient your code is, the more information you will save, the more energy you will save. Okay, understood the question? So see how much of a better code you can design in this manner. And so we'll continue with this next time also, and you'll see how the connection of this topic with some other topics in mathematics. Okay, so that's all for today. I'm logging off. Thank you. Bye.
Excuse me, sir. Uh, Sir, can you share the solution PDF of selection test?
I don't have solution. I have a hints page. So I have 1 or 2 line hint for every question. That I think may be sufficient for you to do the questions.
Okay,
Even
sir.
after that, if you are stuck in any question, tell me, then I'll give you the full solution.
Okay, sir. Thank you, sir.
Sorry?
You don't have the lecture notes for these lectures.
Yes, I have lecture notes. So you like some PDF? Yeah.
Can you share one previous last time?
There is one. See, for a whole power of a point, I have one PDF. I don't have like lecture wise PDF. I don't have. So whole power of a point, coaxial circles together, there is one PDF.
After you complete this chapter.
Then I can share it. Yes.
Coordinate geometry.
Coordinate geometry. I don't know. Does Holland Knight have coordinate geometry? No. Yeah, it is good, but actually it is quite advanced. So I don't know whether that's a good book to introduce coordinate geometry. Where it is? This mouse is very sensitive. Can you see the mouse? I don't see it anywhere. It is not appearing on the other screen. How am I supposed to end the meeting now? Any idea? Okay, fine.